Action. Hello, everyone. It's a great honor to be here to present this work. My name is Le Guan, and this is a joint work with my colleague, colleagues Xu Jun, Wang Shuai, Xin Xinyu, and Professor Lin Ling, Professor Liu Peng, and Professor Wen Keli. Today, I'm going to talk about an attack that towards personalized insurance to get a fraudulent insurance discount, and will also propose a defense system to detect such attacks. So this is the outline of this presentation. First, let's begin with the background. So in a traditional auto insurance, the insurer will typically calculate the premium of its customers, basically based on the historical data, which typically involves the type of the car and the driver's information and his accident and his or her accident history. The result is that this kind of calculation is very static and very it is not a very accurate estimation of the potential risk of this driver. So a customer usually get a fixed premium for a long time. However, there has been a study that shows that there is a very strong relationship with the claim, with the accident claim and the mileage that a driver will drive, especially the behavior of the driver. So here comes the usage-based insurance. In this kind of insurance, the company will calculate the premium basically based on the driver's individual personality and get a very precise estimation of his potential risk. So usage-based insurance is also known as pay as you drive. So it's more accurate to estimate the risk of a driver. It's basically based on many factors. Many factors. For example, if the driver have many hard pulls that have many hard brakes that means he applies the brake very hardly, which will cause a very abrupt speed decrease. That will be very risky, and other factors include hard cornering and fast start, and also there have been studies that show that there is a very risky hour that said between midnight and 4 a.m. on weekend. It's very risky to drive a car, and also there are many places that is very likely to cause a car accident. So the basic idea of usage-based insurance is that a high-risk driver should have their premium increased, and for a lower risk driver, they should get a discounted premium. Because of its advantage, there are many companies, there are many insurance companies that have involved in this kind of service. So, according to a research, approximately there will be 70% of all the insurance carriers that are expected to employ usage-based insurance. Here we can see that for a very safe driver, the amount of the discount that can be granted can be very considerable. For example, Progressive can offer a discount of about nearly 30% for a low risk driver, and for National General, they even grant almost 50%. So our question is that is it possible for a high-risk driver to cheat the insurance company to get a fraudulent insurance? So our answer is yes. Before we look at how we launch an attack, let's first look at how the usage-based insurance works. Basically, the insurance company will distribute a kind of in-vehicle telecommunication device that we call it telematics to its customers, and the customers is required to install that kind of device to its onboard diagnostic connector, and with that device, the device will send a command through the OBD2 connector to the vehicle and get the operational data from the car, and then the telematics will send back the data to the driving data of that car to a remote center, and the remote center is operated by the insurance company, and it will calculate the potential risk, how risky this particular customer is. And to fully understand how this kind of telematic device work, we did a black box, the reverse engineering work. So we got an OBT emulator that emulates the behavior of a real car, and insert the telematic into this emulator to log what kind of command does the telematic send to the car, and also we can also respond artificial information to the device, and finally we analyze the command and the response pairs to understand how it works. So here is a workflow of the how this device works. So it's very small, so you cannot see it. I will briefly explain it to you. We split the workflow into 3 phases. In the first stage, we call it engine ignition. In this phase, the telematic device will detect when the vehicle is failed, and then report the vehicle identification number that is called VIN to the insurance company. And the insurance company with that information can match the registered drivers. And the main body of the workflow is in the second phase, which we call it engine in operation. In this phase, the telematic will constantly query the speed of the vehicle and also the RPM values. And send it back to the server. The last phase, we call it engine shut-off. It will detect that the engine is down, and then enter a low power status to save energy. So now we present our work, our attack. We first present a very naive attack. That is, we first employ a very well-behaved driver to drive a car, and then we wrote an Android app to collect his driving behavior, and then use our emulator to replay his behavior. So in this screenshot, we can see that we successfully treat the insurance company because the company displayed our replayed information. Because in this case, in this trip, we have we have about 81 minutes, and with the speed of more than 160 miles per hour. I think this is definitely a manipulated speed. So we can conclude that there may be potential. There may be an absence of any abnormal detection on the insurance side, but that kind of replay attack is very naive. So if there is some location-based detection, it can be quickly identified. For example, if the telematics have a GPS chip in it, the insurance company can find that the vehicle actually does not move, so it can easily identify this cheating. So we enhanced our attack and employ a so-called online man-in-the-middle attack. So the basic idea is that we insert a hardware module between the telematic device and the car. This hardware box will smooth all the dangerous behaviors on the fly and then replay it to the telematic device. Here is the diagram of our design. On the left side is the car, and the right side is the telematic device. Here is our man in the middle box. So when the car sends the operation status of the car to the telematic device, it first goes through a software on the computer. If that data does not reflect any potentially dangerous behavior, the software will forward it to our OBD2 simulator, and the simulator will respond that to the telematic device. Otherwise, our software will employ some smoother algorithms to remove that kind of dangerous behavior, and then forward it to our emulator. So in our experiments, we assemble we connect all these kind of things into a car, and successfully smooth all the risky behaviors. So actually, the goal of our attack is not to get fraudulent discount from the insurance company. So we stopped our attack before the discount can be applied. But we have a contact with the insurance companies, and they all have confirmed our attack. So let's move to our defense system. The root reason for the above-mentioned attack is that the insurance company does not do any kind of integrity in checking of the cyberspace data. That is the data from the OBD2 the OBD2 connector. So a very simple unobvious solution to this is to add some authentication mechanism to existing vehicles. But the system design of the car is not very familiar with what is like on internet. On internet, we have a digital certificate and PKIs to provide that kind of authentication protection. But it cannot be easily integrated into the existing network in the car. That is called a car network. So we employ another idea, that is to integrate to employ a physically unforgeable sensor that is correlated to the data from the OBD2 data, and then seal them together into a temporary persistent box, and then send a boost of data, that is the data from the cyberspace data. Here is the diagram. We can see it clearly. So we augment the existing telematics with a kind of sensors which is physically unforgeable, and the data from car may be manipulated by the attacker, and the telematic is sealed in by existing technologies, and send the data from the cyberspace cars and sensors together to the insurance data center, and the data center will run some algorithm to find if there is some relationship with this two sets of data. If it finds that the data from the cyberspace is not consistent with what is measured by the sensor, there may be potential attack. So here we model our problem. With the enhanced telematics, the data center will receive the following data. First, it will get acceleration data from 3 dimensions. That is from the forward direction, and vertical, and the left or right direction, and also it will get an OBD2 speed reading. We call it Y1 through Yn. So our goal is to model the relationship with X and Y, and to get a predicted interval from a predicted interval from X, that is the physical space data. And if we found that the received Yi is not within this range, it is not within this interval, we can identify this Yi as manipulated. But we found that to get the relationship between these two data, we found that it's very difficult, because in this figure we can show we found that there are many unobservable factors that is involved to that is involved. For example, this figure in the x-axis it's the vertical acceleration, and y is the speed variation. We expect that all the data will be zero, because the vertical acceleration will not influence the speed. But on the contrary, we found that it's not this case. There are many noises, and similarly, we found that the forwarding in this figure, the axis is the forward direction. We found that we expect that there will be some linear relationship with the forward direction and the acceleration, but in fact they found that still there are many noises. So a single model may be not sufficient to capture all these kind of unobservable factors. And also, for when using a smoother, it has been very well known that it's very poor for the multivariable systems, because in our case we have 3 dimensions. So our solution is to use a mixture of a Gaussian regression model. That is, we will consider and we will model the OBD2 output as the output of an individual Gaussian distribution, with each of which with the mean of the input x multiples covariant beta, and also each component have different variance. So the problem is to use the observed data set D to get an estimate data theta. The theta will include all the component of the Gaussian distribution, and because the number of the components is not unknown in advance, so we use directly process to relax it to infinity, and then use the standard Gilbert's sample to draw the parameter set theta. So here comes the evaluation. We recruit users to collect more than 1,000 miles across the vehicles from 6 manufacturers, and among the 89 trips, 40 trips contains manipulated data. That is the data that is collected from the vehicles that is inserted with our man in the box smoother, and we use more than 14,000 training data to draw the parameter set theta, and then and use more than 76 test data to test the efficiency of our system. The results show that we can get both a very low false negative and false positive. I want to show you here some interesting findings in our evaluation. As I mentioned earlier, we use a mixture of Gaussian models, and here we list the top 10 significant components in this model. We found that there is only one dominating factor, and we expect it to be the acceleration of the motor vehicles. For other factors, maybe it models some kind of bumpers or something we cannot foresee beforehand. And also, it's very interesting to have a look at the influence of the data from each dimension. This is the mean covariance of the mean, that's the beta of the most significant the most significant component. We can say that the mean is around 0.2, and for the lateral direction, it's a little higher, and for the vertical direction, we see that it's almost around 0. So it's expected because the vertical direction will not influence the speed of the vehicle. So our conclusion is that current usage-based insurance service is cannot effectively provide authentication to the data that it collected. So there are many cyber-physical systems that face a similar problem. For example, in a smartphone, there are many rewards that can be granted to the user when he has accomplished certain kind of tasks. So it's quite feasible for them to manipulate that data and send it to the server. So the problem here is that when the device is handed out to the end user, the company will totally lose their control. And we also show the feasibility of using unforgettable physical space data to verify the cyberspace data. That's it now of the talk. Thank you.